Hey, good to be here for another session of engineering design in Omniverse. Please excuse Jen. She's only on her third cup of coffee. I'm not sure if she's awake yet.
my first actually.
Oh,
So
oh, oh dear. That's serious.
we'll get there. We'll get there.
uh, seriously though, if you look on the screen, you'll see a crank slider with a working animation. So that's cool. You see, we've got our position's not working again. Look at that.
But you
Let's,
want to know what else is cool?
yeah.
GTC.
Oh my gosh. I can't wait to I've been cooking as fast as I could for a month or two or three.
Mm-hmm.
We've been really working hard for GTC, all of us, haven't we?
Mm-hmm. Yeah.
And
Everybody at NVIDIA is like super getting cool stuff ready for everybody. Especially for like things like the keynote, their sessions. Like they got some pretty cool things that are going in the back end.
let me get a link for that because I'm signed up. Jen signed up like 3 months ago so she could snipe all the good spots for the hands-on sessions.
Uh,
She's on top of things.
yeah, my schedule's full.
Yeah, so it's at nvidia.com/GTC. And I honestly don't know. I can't remember what I can share and what I can't. I mean, it's like so many like awesome top secret things that we're about to share next
Mm-hmm.
week. And I can't keep, so I'm just not going to say, I'm not going to say too much. And Zha's saying, feels like this GTC will be really big. And I think you're right. It's going to be really, I don't know. Of course, the stuff that I've been working on, I'm biased. I think it's really cool. I can't wait to share it. Um, yeah, it's fun. Been
Mm-hmm.
working, and we got some more. I mean, I'm not done yet, so I'm still cooking some other stuff. We'll
Mm-hmm.
see. We'll see how far we can get. So yeah, register, sign up, join us at GTC this year. I see people are still rolling in. So nvidia.com/GTC, and it's going to be epic.
Mm-hmm.
Let's go back to the crank slider for now, though. And I'm just getting, I had this the other day where I kept getting 4.96, negative 4.97 for every, yeah, I'm not sure what's up. So let's look at those positions in this code here. And let's see what we're doing here. Um, get physics interface dot get rigid body transformation. And let's debug and let's see what's coming in here. I'll start the simulation. And just looking at what I'm doing here. Current transform position 0. So if I go to the debug console, I can just take that line and enter it into the debug console and run it. Yeah, it's 4.97. Okay, watch out. 4.967. It seems like it's just kind of vibrating or something. Oh, I remember what. I don't know why I didn't lose. What happened to it? This should be that's grabbing us the X direction, which is pointed out, and we need the Y direction. And I swear we changed that. Um, but there it is, back to X. Maybe I didn't save the my work. I guess. Let's go.
Maybe it was because in this scene we have um Z up. Maybe the other one was Y up.
Yes. There we go. That's looking better. That's more what I expect. Isn't it interesting to see those velocities are just not what you expect, are they? There must be some vibration going on. Let's make sure it's actually the. Let me. Where are you? Oh, look, that's grabbing. It's grabbing just some vibrations or something because it's once again it's grabbing the velocity in the x direction instead of the y, and so we're just getting some kind of vibration in the x direction, and that's what we're picking up right now. So let's switch that to the y component of velocity and see if that's a little cleaner. Where's the Omniverse? Oh, okay. Well, it looks like it's getting too big. So this one's too small and this one's too big. Let's change those scales and see see how that looks. Let's see. Oh yeah, this has even got the old plots. The velocity needs to get bigger. Let's see how that looks. All right. I think position's looking better. Velocity is still like not.
Are we multiplying the velocity? Like, are we scaling it before
Oh,
appending it?
good question. Let's make sure we're not. Oh yeah. Yeah, this is my old code. Like before we fixed anything last time. I don't know what happened. It's like I wonder, I restarted my computer to install some updates, and I wonder if if I just forgot to save everything. But I swear you have to save before you run. So I'm just a little baffled, but I'm glad you caught that. So now let's bump velocity back down, and let's just go from like 50 to negative 100 because it's kind of like it's not the position's not based off of 0. Let's see how that looks. Just tweaking. Oh yeah, that's looking better. I'll probably just call it good right there. I mean, it's not like centered and whatever, but I think it's looking pretty good. Okay.
Good question.
Position varies, but velocity is constant. Is that right? No, because if you think about it in its cycle, let me see if I can get the window physics. No, let's stop here. No, it's going to window simulation debug. If I go into the physics debug, we can step. Oh, it's not giving us some bugs, but if you think about it, right now the velocity is 0. It's actually switching directions right now. Now the velocity looks like positive. Now it's 0. It's negative. It's 0.
Acceleration would be constant, right?
No, because right now it's going to be acceleration will also be 0, and it's going to change direction. So it's going to actually decelerate, and now it's going to accelerate, decelerate, stop, accelerate in the other direction, decelerate, stop. So yeah, nothing. None of those are constant actually. Oh dear. And we got this thing. Luckily, I was careful and made sure that if you take the steps with that physics debugger, it kind of it changes your kind of initial position of stuff. But you see these translates. If we just kind of oh dear. I'm just going to reopen the scene. Let's go to don't save. There we go. Let's relaunch that extension. Yeah, I think he didn't like me reopening the scene. So there we go. And also, let me think. I always get this backwards. We got position, velocity, and acceleration are all related by calculus, by derivatives. And so let me think.
So acceleration would be like x squared, or no, x something, take the derivative of that, you get velocity, take the derivative of velocity, you get position.
Yeah, or the other way around. Are you sure about the direction you said?
Yeah.
Okay. Here we go. See how it also says velocity is a derivative of position. So that means acceleration would be the derivative of velocity. And so I haven't found an API that lets me directly query the acceleration yet. It doesn't mean it's not there, but I haven't found it. So for this velocity plot, we'll take our position, or excuse me, for this acceleration plot, we'll take our velocity and then differentiate it as we go. So let's work on that. So here we've got, so what we'll have to do is we've got, let's see here. Here's our velocity. And so we'll say self dot underscore previous velocity is equal to, actually we'll call it, say, next velocity is equal to velocity 1. And here we'll say self dot underscore next. So we're just going to grab that velocity component and put it in there. And then we'll do in our initialize previous velocity equals 0. Well, we're going to need that here in a minute. So we want an initial value of 0. And where are we? Grade our velocity, set our velocity. And we're going to say acceleration equals rise over run is going to be self dot underscore next velocity minus previous velocity. And we finally get to use delta. That's the time step of our physics simulation. And then we make sure and save our previous velocity is equal to next velocity. So we'll keep updating that previous velocity. It's too early in the day for calculus. That's true. Luckily, yeah, it's a little early. All right. Did we set that one all to 0? The acceleration data. Great. So now we can say self dot underscore acceleration data dot append self dot underscore. Oh, this is kind of the wrong spot. That's okay. I'll just copy and paste it here in just a second. I'll need semicolons in Python. I did a little bit of C# coding yesterday, and it got me all. I've done so much more C# that after like an hour of C#, my mind just like snaps back to C# everything. Let's not a comment. Great. So we append that. We're going to want to do this pop thing here for the acceleration data. Great. And then we'll want to append it to a plot. And who knows? It could work the first try, right? It could happen. Oh, apparently our accelerations are large in magnitude. So let's change our scale there. Let's see here. It looks like way big. I'm going to add 2 zeros because I'm just maxing it out, right? Okay. Apparently I didn't need 2 zeros. That was too much. Oh dear. And whoa, cool. Look at that. That's really interesting. Oh, why did it stop? That's weird. Oh, what?
You have an invalid argument in your console.
Oh. Let's init up. Weird. Let's just
it looks like the step event has kind of screwed things a little bit, maybe.
let's just reload the extension and see if that fixes it. No. That's odd. It was working and then it wasn't.
Well, when you turned on the debugger, it seems like, or the physics debugger, it might have screwed some stuff up.
Yeah. Let's try reopening the scene here. And then let's restart this and let's oh. It's not even loading right. What? That's weird. Okay, what's it saying now?
Failed on shutdown.
Oh dear. Well, all I do is print the name. That should be fine.
What was the error?
The weird thing is it's still visible. Invalid argument. On shutdown extension. I'm just gonna relaunch Omniverse, I think. Can't go smooth, right? Why would it? You gotta.
Yeah. Live streaming do be like that.
Yeah. It's like I haven't had any trouble all week. I mean, there's trouble, but I feel like the live streams are definitely a lot more problems than if I'm not live streaming. Alrighty. So now if we run this, looking good. Let's go to no errors that I can see. I don't know. Some kind of mystery. It was like exactly halfway when it died last time. Yeah, I'm really curious about the shape of that derivative, honestly, that's not passing the logic test for me.
Actually, all these are kind of curious, right? Because if you take the derivative of position, if your position is like uh, squared, right? Then your velocity should be linear, and then your acceleration would be constant. But in this case, they're all.
Well,
I guess
this one seems pretty linear.
that's true.
And let's think about this. So the rate of change of this. Well, and that's not always true, right? Because if this is more like a sine function, then the derivative would be a cosine function. And then the derivative of that would be a sine function again, right? You're thinking this is a polynomial function, and I don't think it is.
Oh, too early for calculus. Well,
what's the derivative? What's the derivative? So the derivative of a third degree polynomial. So the derivative of x cubed is 3x squared, right?
Yes.
And the derivative of 3x squared is 6x. I think that's what you're thinking of, is that you go from, and the derivative of 6x is 6.
Yes.
And so I think that's what you're thinking of, is that it's like a polynomial, that this first one is a polynomial function. And so the second one is should be a linear function, and the third one should be constant.
Okay.
And that's which makes sense that you would think that, but it's totally wrong.
Yeah, so if you're thinking of sine and cosine, so the derivative of sine is cosine, but the derivative of cosine is negative sine.
There we go. Yeah. And we're more in that territory.
Right. So does that mean that
but not exactly, right? Just remember, it's not exactly. Well, I mean, how about if we Google it? Like, let me just. I wonder if I can find a plot. I'll pull it up here. Let's just see what we can do here. There we go. Let's see what this one talks about. I think it's going to be more, because you look at this. This is going around a circle, right? So I think it literally is going to be. It's going to be some kind of a trigonometric function, because you look at this, and it basically the XY position of this slider is directly related to just the X component of this. It's going to be if you look at this thing, this triangle, it's going to be this side here. So it's like it's dead on. It's going to be cosine. It's going to be a trigonometric function.
Oh, right? So I can't copy Zia's link, but I can paste it to you over Slack.
Yeah.
Because they were saying that they were looking for more like this. So that's interesting. I don't know if you got the link.
Did you send it to me on Twitch or something?
Oh no, I sent it on Slack.
On Slack, I mean.
Yeah.
Let me see if I can. Oh dear.
Oh! Secrets about me making coffee.
Yeah. Here we go. No secrets in that one, luckily. All right. Um.
I'm not
So
sure if you
what's this
can
paper?
interpret that. I guess they were hoping our graphs would look more like that.
No. What paper is this? Particle dynamics. Yeah, we're looking more at something like this. This is your classic analysis of a crank slider. And here, this is the crank. Oh, here's the crank angle, which is in degrees. So here's the velocity of the slider, which actually looks a lot like ours does. And the acceleration looks like the classical analysis of crank slider acceleration. So that's kind of wild. I mean, ours is inverse of that. But yeah, it's totally, I think we nailed it, actually.
Mm.
Cool. So I'm thinking of why does it do that? It must, like, as it's coming around on the one side,
Yeah.
it must kind of like slow down and speed up. It like so it's slow. It's accelerating and decelerates and accelerates and decelerates. That's wild.
So I wonder if you start playing with some of like the
And I get this glitch, boom, because I'm starting. I think that's just because I'm starting it with just throwing a 0 in there for its
yeah,
initial
if
acceleration, which is probably wrong.
if you start changing with the masses, how would that affect the graph?
Not at all.
Oh.
It wouldn't affect it at all.
Hmm.
This is my all-time favorite of generating a sine wave.
No, I could send that to you. I I also looked that up. It kind of looked really neat.
Yeah. Let me see here. Well, cool. So this is the question. So, but what do the masses affect? And the masses affect the forces. So we're just moving this thing without respect to how much it weighs.
Hmm.
But the force of the slider on that white pin, the force is equal to mass times acceleration. So we're going to take this acceleration at any given point and multiply it by the mass of this slider. And that is the force on this pin in the y direction.
Okay.
And then we're going to use that force. Let me just get a top view here. Can I do like just a top? Yeah, I totally can. Here's a good spot. So that force is going to push in, be a great extension
Hmm.
just to be able to doodle on the screen.
I've thought about that since day one.
Oh my gosh. Okay, so we got a few people watching. If you want an extension that would be so useful, but I think that it wouldn't be super hard to write, we're just too busy. Write a little, just like a little, put a little color picker there so you can pick a color, and then maybe you could even just start there and let people just like draw on the screen you can, oh my gosh. Yes, there it is. We need a John Madden whiteboard. Just like, yeah, that's exactly it. So somebody please, here we go. I have wanted that for video editors.
Mm-hmm.
Yeah. So I really hope one of you will pick that up and write it because
Yeah.
we need that right now. Here we go. If you write it, we'll invite you onto the live stream to show it off. Okay.
I mean, that's
Show
a
us how it works.
guaranteed.
Yeah. I just really, we just, and we'll use it all the time because that would be so handy. Okay. Just a second.
Got super excited.
How do you write on the screen? You know what? Isn't there a GTC session where we're going to teach people how to do scene decorators?
Scene decorators.
How to like draw on the screen? Do you scene? No, maybe not.
You know, I don't know because my schedule is very weird. I pick certain ones. There probably is if you look for one. I guarantee to you there probably is. I'm just was oblivious when I was looking because there's
All right.
so many sessions. There's so many of them.
So I don't know exactly how. I know you can do it, and I think if you reach out on Discord, I bet you could get some. You could get some good
Yeah.
help there.
I think something to consider if you're trying to start off with is you would want to create something similar to what Maddie does for his reticle, but instead you would want to start drawing like kind of like how the plot UI comes out too, right? You figure out
Yeah.
how they're getting the lines to get drawn like that, and then combined with how you can add to the viewport as like a second like layer that you can turn on and off or something, and then go from that.
Yeah, I think annotations would be really great. But if you look at this Y component, so we're going to have a mass times acceleration pushing against this in this direction. All right. That's, if you think of a triangle here, we find this angle, and it's going to be, see, the cosine is going to be the or sine is opposite over adjacent. Opposite over adjacent. So we know, so that vector length right here. So we went on we want the tangent, which is
Wait, opposite over
no,
adjacent?
I'm sorry, opposite over hypotenuse.
Hypotenuse, right? You were going tangent.
Yeah, sorry. Opposite over hypotenuse is the sine. Cosine is adjacent over hypotenuse. So the
Yes.
cosine of this angle is this component. So the arc cosine, I'm forgetting right now, but basically, oh, I gotta kind of write this down now. Let me see here. This is where I'd usually just go on to paper. I do better on paper with this sort of thing, but let's grab Excel instead. Too early for trig.
Yes, it is very too early for trig.
All right.
Oh, we're bringing out the Excel, not even MATLAB. We got
Sine is
Excel.
equal to opposite over. Oh, sorry, we want cosine is equal to adjacent over hypotenuse, right?
Yes.
And we have adjacent, and so that means that, or so let's say cosine of theta. That means that theta is equal to the r cosine of let's see, theta. Oh, no, here we go. We know adjacent. We want to figure out hypotenuse. So that means that hypotenuse, so it's equal to adjacent over cosine of theta. There we go. It's actually not so bad. Going to swap the hypotenuse and the cosine of theta. So that means if we take this force and we divide it by the cosine of this angle, that's going to give us the force along this thing. Okay? And we will apply that force. we'll fix this central pin in our imagination, and whatever force is applied to this guy, we will apply it to this crank rocker. And we'll figure out the angle of the rocker, and then we'll apply the force in that direction. And we can use that to apply loads to the rocker in some structural optimization software and do a structural optimization on, I guess I'm calling it a rocker, but it's a crank arm.
Yeah.
We'll apply those loads to the crank arm. We'll do a structural optimization and come up with a really cool looking crank arm.
So we're trying to find out what the hypotenuse is?
Yeah, well, we're trying to find out. So the load so when we apply the force, when we find out the force from the acceleration, we're only looking at the y component of this acceleration. So it's going to give us the force just along the axis that this is going. But that's not how the force is transmitted into that arm. That force is transmitted along this linkage.
I see.
And because we have a force in this direction that we have to provide, when that linkage is at an angle to what the force we actually have to provide, the force along the linkages is actually bigger than the force that we actually gets transmitted into that slider. And so we got to make sure we apply the actual bigger force to our arm, or else it would just be the wrong force.
I see.
And we got to apply it in the right direction because, for example, right here, nailed it. Good spot. It's actually pulling, it's actually pulling on that, right? But actually at the next step, I mean, think about that. And so right here, the force along this link is pretty much the same as the force as the force on the thing, right? Because they're kind of aligned in that X direction. But it's kind of weird because, yeah. Where is that force going to be biggest? Right here, the force is going to be quite a bit bigger.
Yeah. Also, I made a fun diagram.
You did?
I did.
Where? Can you
Slack.
Oh,
I was trying to actually do the doodles in Paint.
Oh, I can't. Let me see. Let me.
In case some people are having a hard time following along in the Excel.
There's your sine wave. Is that what you want?
Oh yeah, that was the sine wave. No, it was
Oh
the
yeah,
one
yeah.
below.
Okay. Let me.
I'm also drawing with a mouse, so it's not good.
There we go. There's the adjacent. There's the hypotenuse. There's theta. Yeah. Hypotenuse is equal to adjacent over the cosine of theta. That's right. Trig and calculus in one day, in one morning.
Oh.
Where'd you guys? Oh, our numbers are dropping. Just kidding. I'm glad you all came.
Okay.
Let's see here. Clear it. Stop it. Run it. I just love watching those plots. Okay, so let's do this. Let's think about this. Because the next step, I'm sorry, Jen. I think we're going to have to do some vector math.
No! Okay. All right, I'm ready.
All right. Let's see here. If we take the position in space of these three things, we don't want this one stays the same, so that's nice. We've got the position of this rotating shaft. We've got the position of this pin on the slider, and we've got this position of this guy. And if you take, let's see, if you take the vector from here to here, from the white one to the blue one, and if you take the vector from the white one to the yellow one, and if you take their dot product, which isn't too bad, that gives us the angle, but I don't think it's like the sine of the angle or the something of the angle. Let's see. I'm Googling dot product off to the side. Let's see if here we go. The theta, the angle between two vectors, is the arc cosine of the normalized dot product of those two vectors. So you dot product the two vectors, you divide it by the length of those two vectors, and then you take the arc cosine, and that gives you the angle between two vectors. It's not so bad, right? Is that so terrible?
Yeah, no,
Jen's,
it's bad. Brain. The only time I ever used dot product was for game stuff, where if you're trying to figure out if something's behind you,
yeah,
or in front of you, you would use the dot product, and depending on if you got a negative or a positive or zero, depends on what direction it's coming from.
yeah, it makes sense. I love this. Let's do it. Could
Yeah.
we plot it in real time? Yeah, let's plot theta. Why not? So let's go in here. Let's go back to our beginning of our thing. Oh, this is the coolest plot name ever. Theta data.
That's
Come on. That's good, right? That's good.
well, I mean,
It's
Zia's giving you a +1 for that.
That's not just a dad joke. That's a dad math joke. Isn't that bonus points or something?
No.
No, no bonus points.
No.
Copy this. And line plot. Let's see. Pi divided by 4. What's pi divided by 4?
In terms of like cosine or sine?
In terms of decimal numbers.
Oh.
0.78. So we're just going to go, this one is from negative 0.8 to 0.8. Because pi force is 90 degrees. No, it's not. Pi is 180. Pi halves. Sheesh. And we're going to go theta data. Right, the 100, a centered, looks good. So we added a new oh, hello. Give it the same name. Data plot. Reset theta data if we need to. And reset theta plot to be attached to theta data. It's like a tongue twister. Try saying that 5 times fast. Theta data, theta data, theta data, theta data. Oh, we've got a few people. We got Julio and Intermix Hector and bienvenidos. I actually speak a fair amount of Spanish, but not technical Spanish, more like hang out and talk about cars Spanish. So we'll stick to English for the live stream.
Yeah.
Theta plot. Like hanging around. Sorry, no Portuguese. You know, the interesting thing about, well, I don't know, there's like, Portugal Portuguese and Brazilian Portuguese, which are, I know they're the same language, but they're a lot different. But people, in my experience, Brazilian Portuguese speakers can speak Spanish and understand Spanish pretty well, but it's like this one-way street where it doesn't go the other way. If you learn Spanish, it doesn't. You just don't understand Portuguese at all. Whereas, like my brother lived in Brazil for a few years, and he could speak decent Spanish just for whatever. I don't know why that works that way.
Yeah.
All right, let's see here. Back
But
on.
also, the best part is in our Discord, we do have a Portuguese channel, and Papa Chuck is very,
Oh yeah,
um,
right.
he's very,
Active.
yeah, active in the Portuguese channel. So,
And he's Brazilian, is that right?
I don't know. I don't remember.
All right, we've got our plots now. I like this view. It's kind of a nice view of it, isn't it?
Yeah. It's easier to visualize it when
Like what's
it's
going
in
on?
2D than in 3D for me.
Yeah, well, yeah, that's the funny thing. It's the 3D thing, but we're really doing all 2D math here, which is good. Oh, Chilean. I lived in Argentina for 2 years.
Oh, wow.
Let's see here. Where are we at? All right, we're gonna have to, let's see how far we can get. We got 15 minutes. And we're gonna leave the generality of this, by the way. But that's okay. Because so far it's like a general extension that you could use to write an accelerometer for a prim and just attach it to any prim, which is kind of cool. But we want to get those forces, so let's just keep going. So we're going to need to get. See, there's this self.get permanent path. Let's grab a few. Let's see here. Let's grab like where are we at here? This is all the acceleration stuff. And what we're going to want to do is they all, see, they're both vectors go from this white pin. So we're going to call that A. Oh, but A is the same as the position of the slider. Dead on. So we'll just use that slider position for A. Great. And it only moves in the Y direction, so the Y position is enough. No, we need all three. But we have all three, so we'll just kind of keep moving. Oh, if you look at the link, it looks like if I select the link itself, let's see. Oh, it doesn't know what to do. So we wanted to get this pin, right? We'll just do it from the start. So let's grab this pin first. We're going to copy prim path. We'll go into VS Code here. Oops. And for that path, we're just going to put in the string path. There you go. Make it a string. We're going to call that capital A. And let's go back to our scene. This pin right here, we'll copy its path. and we'll call that B. Go to the next line here. And, oh, just a second. What's this? Oh, wrong one. Something good to know is that the position of the black element in correlation with the rotation of the green element. Oh, cool. So that would be a really handy relationship later on if we wanted to start to figure out maybe the torque applied to the to that shaft or something. That's cool. All right, so now let's get the position of that shaft hasn't changed, but I don't know. We're not going for, I don't really. I think it's fine if we just grab it here. So here's that shaft. Let's copy its path and back to VS Code. And there we go. That's the shaft. We're going to call that C. Oh, Julio says, what are you doing? Great question.
Magic.
Magic. So if you look at this scene, let me, God. So if we take the vector from, so this is A, and this is B, and this is C, and we get the positions of each of those, B minus A, we'll call that AB, and C minus A, we'll call that AC. If we take the dot product of AB and AC, that gives us what we need. We'll do some arc cosigning stuff, and we'll get the angle between the angle of this shaft, right, or this link right here. And we're going to do that right now. So, where were we? We've got the position of A, the position of B, and the position of C. And we have their full transforms. So is there a vector library in Python that lets us do this like a dot product out of the box?
Oh, for dot product?
Yeah.
I think that's part of the math library, or if you're getting vectors, like if these are all like vec3ds,
Yeah.
I think there might be one.
Let's just do it by hand. So what we can do here is say, we want to say, this is the current transform, right? We want to actually grab the position from that. There you go. Now, before they were the whole transform.
Zia said NumPy. That is a possibility, but it depends on the formatting. Since a lot of USD uses a vector 3D, which is supposed to be like a vector and integer form, sometimes it already has its own built-in format since it's its own type of data.
That's fine. We'll do it by hand. It's not hard. But if it was a cross product, I would dig for it. Products are a pain to write. Uh-oh. Let's see, I have math errors. I have a couple here. I gotta switch these. It's gotta be B minus A here. Right. AC now, the same. Oh,
You did it again.
did it again. There we go. Okay, so that gives me those two vectors. And dot is equal to AB 0 times AC 0 plus AB 1 times AC 1 plus AB 2 times AC 2. And then length AB is equal to you get the length of this, so it's times AB 0 plus AB 1 times AB 1 plus AB 2 times AB 2. And check up on me. I'm likely to make a math, like a little typo here. So need everyone's eyes. We're going to do this in 4 minutes. Let's see. So this is the length of each of those. And so that means that theta is equal to, where was that? I had it up. All right, dot product. Here we go. Theta is the arc cosine of x dot y divided by the magnitudes of those vectors. Dot divided by length AB times length AC. That should be theta. We should say self dot underscore theta data dot append theta. You better clear out theta data and append that to the plot. Hey, in theory, that should work. See how it looks. Nothing's working. Key error position. All right, let's look at what did I do wrong. What is the difference between a single quote and a double quote in Python?
Good question. I usually have it in my brain and I don't think about it.
Yeah, check it out. So what it's saying is it doesn't like, it's giving us key error position on line 138, which I just stuck this on so I grabbed the rigid body transformation, I'm grabbing the position. Oh, hello. No. Current transform. RV success equal to current transform. Current position.
Oh, okay.
Oh,
So I figured it out. It's okay. Yeah, this was like a thing that I usually just I don't think about. So if you are using both single quotes and double quotes represent strings, but if you are going to put single quotes inside of your string, you should use double quotes.
okay. I'm just wondering why is it so this line's working here. I guess maybe it's failing. RV success, don't need that. It's equal to current transform return val. So I wonder if it's failing to grab the transform for some reason. So let's see here. Just a few lines, I think. We can debug it a bit. Oh, no. I don't know why it's not working. All right. I'm going to put a debug stop here. Attach the debugger. And let's just take a look. See what we can see. Okay, it just died. Doesn't like it. Let's take a look at a transform. Oh, return value is false. It's failing. So, because if we look at current transform, its return value is true. Oh, shoot. So let's see here. Let's see if anyone has any hints or tips or. Yeah. I mean, I think I would change this to NumPy, by the way, Zia. If I was going to, I just want to get it to work right now. And yeah, so this get physics interface dot get rigid body transformation. Oh, you know what it is? Those are meshes, and so they don't have rigid bodies.
Mm.
So that means we'll have to look in and see if we can find a different way to query those. And let me just show you, and then we'll wrap up for today. But if you look at, let me get this going here. If I stop this, the rigid body is right here on the crank. So here's the rigid body. And we are currently using the physics interface to try to grab the rigid body. However, we're grabbing it from this guy, which is not a rigid body. It does not have a rigid body. So we can't query the position that way. And so we'll pick up there next week. I think what we can probably do is use USDRT to just query the position or the transform attribute. I mean, right there, you've got transform OP, transform. So we'll be able to use that to grab the position of those prims. So we'll do that next week, though. We'll do that next week. We can probably even add like a, oh dear. Well, I'm not going to mess with that right now.
So good questions. Do we need an X form?
I think that let's look at the crank. It's got a translate, scale, rotate. And so I believe we can just grab, well, let's just, do you have like a few more minutes? Let's do it. Come on. We got to.
There's also another good one. Can we get the code so far somewhere?
Not yet. I should probably, I've been so busy with GTC that I haven't done that yet. But I think what I should do is go ahead and I'll go ahead and get what I've got so far going through the approval process to publish. So I think it's getting, especially once we get Theta up, I think we'll just create a GitHub repo and kind of update as we go.
And are we broadcasting next week during GTC?
I'm going to look at the sessions Thursday at 10 a.m. And I'm thinking what we might do is just do like either do more like a watch party. If there's a session that's kind of pertains to this, then we can watch that together. If not, maybe we could watch the keynote together again. I watched the keynote a couple of times, and so that's another option. I'm curious what you all think. Would you rather watch a session together, or would you rather watch the keynote together, or would you rather just keep working on the crank slider? So yeah, let me know what y'all think. But what we can do here, let's get the we call this A prim. And then we're going to go right here. And then we'll copy this bit. This is using USDRT to get the prim. And then we have the some of the attributes. And we're going to say oh, we don't, that's not what we want. What we can do here, the nice trick is that we can go in and we have the translate. Oh, we want the shaft. Let's see, add transform transliteration scale. Oh, let me think about this. I think we're just gonna let's just right click on what it's got. Oh no.
Yeah, there's two different ones. There's transform, which has a matrix 4D, and then the other one is broken into translate, rotation, and scale.
Yeah, so my question is, if I add a translate rotation scale,
it's going to be based off of the current position. So everything's going to be zeroed out when it's not.
And then, but if I move this, that's what I have trouble with. I just translated it.
They're independent.
So if I query, which do I get? Or which one is physics update? I think I'm just going to have to work with the transform that's there. So the attribute is called transform OP : transform. Can I just disable, delete? Oh.
Is this becoming more complex than you originally expected it to be?
Let's just see what happens there. I just deleted the transformation matrix and just put in transforms instead.
Oh,
What does that do?
I don't know. If you press play, what happens?
Let's find out. I was gonna do that too. Well, if I press play. Oh no, that's okay. Don't do that. Don't do that. Abort. Abort. Oh, come on. I broke it. Let's reopen the scene. Heavens. Don't save. There you go. Top. That was a nice camera. All right. We'll just work with the transforms that are there. And I think it's X form OP colon translate. I think. Take a look. Geometry slider geometry. Let's see.
So is the simulation transform is not the same as the transform property of the prim as we normally know it?
Yeah, I don't know. It sure broke it though, didn't it? I'll have to look into that. It's transform OP colon trans X form capital O colon transform. It's capital O. Oh, transform. We want it to be A prim. Double check that those are set up the same way. Here in the link, we've got these two pins. They each have a transform. Yeah, and I think, sorry, Jen mentioned this. I think you already said this.
Mm-hmm.
Yeah, and I don't understand how those. It's almost like however you set it up first, that's what kind of what's connected. I bet if you deleted the joints and then changed your transforms and then reattached the joints, I bet it would work. You know. But the fact that I deleted that attribute while after it was all rigged seems to have broken it.
Here's might be a good answer to it.
I think it depends on what you're used to. As far as I can tell, it comes in quaternions by default. Now, this is actually a transformation matrix. So it's a 4x4 matrix where like these three are your translate. These three are like together are scaled. And so all your translate, rotations, and scales are kind of built into this 4x4 matrix.
Here's also another. This is kind of interesting. What do you think about this question?
May I suggest something? Why don't you calculate the angle theta from the horizontal metatopsis of the connection of the orange element to the green one? Yeah, I don't know how to do that, but it's probably a great idea. And we're really close on this one. Because if you look, so we've got the transform, and if you recall, we may not have made note, but these three are the translate. So it's actually pretty easy. Metatopsis equals movement. Yeah, but if we just grab the fourth row and the first three elements of the fourth row, that's going to be the position of each of those vectors. It's pretty easy to grab the position out of a transformation matrix. Some other things can be scale and rotation get a little kind of mixed, if you will, and they're a little harder to grab out, but not terrible. But let's have it here. So A transform 3. That's actually going to be fine. It's going to give us all 4 elements. So these are going to be a 4 element. Oh, there you go. So now we're grabbing that, and the rest of our math should work. Let's see how it goes.
And if it doesn't, you're just going to have to wait till next time.
Oh dear. USD attribute is not subscriptical. Page line 148. Where are we? Oh, it's not subscriptable. Oh. We can't grab it quite that way. How did we do it before? I don't know. Let's find out. So it's saying, hey, we can't grab the third row of that. We can't use subscripts on a transform. So I'm not sure how that's laid out. Let's find out. If we save it to relaunch the thing and then we start the simulation, we'll get a stop and we can look at a transform. Oh, we've got to call get. Of course. I didn't call get. So we can say
You could do it right there after the get attribute.
Oh yeah. Either place, right? Capital G. Cool. Let's try that now. Save it. And run. Oh dear. Whoa. It's not failing, but it's not giving us great numbers. So let's find out.
You should find out next time, though.
Yeah, that's a good point. We're way over time. Sorry, I get sucked in. We got a bug. It's not working. It's not crashing, but we probably got a bug somewhere in between here and here, I would think. And so we'll figure that out next time. So I'll send a post out saying what we're going to do exactly, whether it be like a watch party or continue with this, depending on the sessions that we've got going on at this time next week. So until then, have fun writing extensions.
Mm-hmm.
I need some kind of like a tagline or something,
One day.
I'll get there. Hey, see y'all later.